So I calculated the energy associated with the inward movement of chloride ions, and I got, make sure I do the right number, I got minus 0.726 kilocalories per mole. Does that sound pretty similar? Pretty close enough, right? The sign, what I'm really important, the important part here is the sign. So where's chloride going to go? Into the cell. What's going to happen to this voltage? It's now it's minus 60 now. What's going to happen to it?
It's going to become more negative.
It's going to become even more negative. Let's say, just for the heck of it, we start out at minus 60 millivolts. Before GABA came around, and now we end up at minus, let's say, 65 millivolts. Is this neuron more excitable or less excitable? Less. And if you haven't had physiology yet, one of the things you will discover is that when you make a membrane even more negative, in other words, you hyperpolarize the cell, this cell becomes less excitable. Really hard to get a nerve, harder to get a nerve impulse where an action potential started. So is GABA an excitatory neurotransmitter or an inhibitory neurotransmitter? Inhibitory. And you didn't need to know anything about GABA to figure out that it's an inhibitory neurotransmitter. You calculated that it's an inhibitory neurotransmitter. Okay? So benzodiazepines work on GABA receptors. So probably your favorite benzodiazepine is Valium. And I would issue Valium at the door, you know, on test stages, kind of to calm you out. The benzodiazepine major effect is to keep the channel open a little bit more. So what's going to happen to this neuron? This neuron, it's going to become pretty inactive. And if I could give you guys Valium at the door, I would. You'd probably be more relaxed to take the test.
So you said the movement of chlorine is going to be outward?
Pardon me?
So chlorine is going to move out?
No, it's going to move into the cell. So negative, because the inward movement of chloride releases a little bit of energy. So it's going to come into the cell. So chloride will move into the cell, and then this cell becomes more negative with the movement of chloride into the cell. And that makes it more difficult for this cell to have an action, to generate an action potential. You take a lot of sodium. Okay.
For the volts going from negative 60 to 65, how did you calculate that?
Oh, I guessed it.
Okay.
I just said, let's suppose. So there's nothing magical about that number. It was just hypothetical. And I'm sure somebody has measured the change in voltage, the change in the resting state.
So because the change of G in was negative, it just makes it more negative then?
No, it's because chloride itself is negative. And when chloride is going to move down its concentration in electrical, you know, the negative sign means chloride is going to move in spontaneously.
Okay.
That's what that negative sign is saying. And the fact that chloride is a negative ion means that the influx of chloride ions makes the inside of the cell even more negative. Okay? Okay, so I'm going to give you guys let you guys take a crack at the practice problems that I handed out. I will take a PDF file of my solutions and then put them on Scholar. And that might not happen for a while, like till later this afternoon, but I'll get them there. Okay. It appears that we need to be moving on to pumps that do active transport through ATP with ATP hydrolysis as the energy. And about all I will get through today is just listing the different kinds. Okay. So interestingly, I like this class of active transport things and molecules mainly because they don't all do active transport. They fall under this category because of their structure, not necessarily because of their function. Okay? As you will see when we start naming them. We're going to be looking at, there's actually 3 different kinds based predominantly on their structure. And to some extent on their mechanism too. Because their structure does determine mechanism. One is a P class. ATPase. Okay, and we're going to call them ATPases because they break down ATP. So they do active transport, well, or have the capacity to do active transport. And they hydrolyze ATP to provide energy. Okay. The old name for this class is E1, E2. ATPases. And it's probably the name that I tend to fall back on because that's how, I didn't learn it that way, but it eventually became known to me as that. It got its name because these kinds of pumps alternate between 2 conformations, an E1 conformation and an E2 conformation. Okay, E1 is not phosphorylated, but E2 is phosphorylated. Okay, so it's called the P class of ATPases because it does become phosphorylated. But its initial, the name of the class initially was E1, E2 ATPases. So I sometimes describe pumps as E1, E2 ATPases rather than P class ATPases. Examples that we're going to look at are the sodium-potassium pump, belongs in this category. And we're going to look at a calcium pump in the sarcoplasmic reticulum of both skeletal muscles and cardiac muscle cells. Okay, so that's that class, and we'll cover both sodium and potassium pump and the calcium pump. So another class is actually 2 classes combined into one, F and V class ATPases. Okay, and they are definite, well, they're all transmembrane. I don't know how to draw this smartly. all of the ones that I know of are actually moving protons. And the protons kind of wind their way through the transmembrane domain and make their way out. And the big ball on the other side is hydrolyzing ATP.
So then is that big ball on the outside of the cell or the inside?
Well, this would never be outside, inside. This is never found on the cell membrane,
Oh, okay.
okay? Okay, this would be, here's where we find them. Find them in the inner mitochondrial membrane. Okay, but you have never seen this protein used as a proton pump. Okay, so this is a proton pump. ATPase, or I would call it an FOF1 ATPase, because FOF1, the bulb on one side of the membrane and the transmembrane domain have different names. One's FO and one's F1, so it says FOF1 ATPase. But what's going to happen if you reverse the reaction of this particular transporter? Just reverse everything. What's going to happen? Instead of breaking down ATP, you make ATP, and instead of pumping protons up a gradient, you let protons go down a gradient. Have you seen that kind of an enzyme before? Yeah, you've called this ATP synthase. And I have a hard time calling it ATP synthase, because to me it's an FOF1 ATPase, meaning it belongs to that F class of proton pumps. Okay? But here's a great example that all of these transporters can work in the reverse direction. So if you took this protein complex outside of the cell and do some experiments on it, you can run it backwards. In fact, that's how we've understood its mechanism, and that was by running it backwards, having it break down ATP while pumping protons. Okay, another one. So this, by the way, would be in the mitochondrial matrix.
Dr. Singer, how does the protein know which way to go?
Well, it's because you pump such a steep, the electron transport chain is pumping because of, also because of orientation. So you pump the electron transport chain creates a proton pump, or a big proton gradient that can, so actually the best, most energetically favorable direction is to make ATP and move protons back down the concentration gradient. But if you had very little protons, okay, if you had very few protons on this side, you're going to do the opposite. Or actually, if you had very few protons on this side, you would do the opposite. If you had more ATP, then the proton gradient, you're going to do active transport. So you have to measure the energetics of the proton gradient and the energetics available in ATP. And then you can, and that'll determine the direction. In other words, you got to do the delta G stuff. Okay, lysosomes are very acidic on the inside, okay? So on lysosomes, the proton pump that makes the lysosome acidic is one of these. Okay? So yeah, the thing that, so ATP synthase does belong to this class of proton pumps, but under physiological conditions, the energy favors the synthesis of ATP with the movement of protons down the concentration gradient. Okay, and then the last class of everything, oops, I would spend more time on, but we don't have time. Our class of, the class of proteins called ABC transporters, and ABC stands for ATP binding cassette. I don't know how to spell cassette. Something imagine. Almost all of them are structured very similar. And most of the proteins have a couple ABCs, ATP binding cassettes. Okay. Some of the multi-drug resistant proteins that are turned on, whose genes are turned on in late stages of cancer, are these kinds of proteins. And the ABC transporter pumps chemotherapeutic drugs from the inside the cell to the outside the cell. Okay, so the drug gets into the cell, and the multi-drug resistant pump pumps it right back out. And so that's how cells become resistant to the drug. I would say that cancer drug resistance comes in many mechanisms. This is not the only one. Malaria tends to be very resistant to some drugs, and that's because they have turned on a gene that codes for a multi-drug resistant protein that will pump the chloroquine or whatever the drug is right back out. The cystic fibrosis chloride channel is a chloride channel, so it can't do active transport. Because it's a channel. And when the channel is opened up, chloride moves down a concentration gradient. So this protein does not do active transport. The hydrolysis of ATP controls whether the channel is opened or closed. Okay, so it's structured like a multi-drug resistant protein, and in fact, that's how it was. That's exactly how it was discovered to be a chloride channel. But the ATP hydrolysis doesn't do active transport. It controls the opening and the closing of the pump. And then the other class, which is really weird. Okay, those proteins that flip a phospholipid from one side of the cell to the other side of the cell, or from one side of the lipid bilayer to the other side of the lipid bilayer, those flipases belong to the class of ABC transporters. Okay, so we're just going to focus on these. Okay, do you talk about this ATP synthase in biochemistry at all? Oh, good. It's just super duper complicated. So I wouldn't talk about it either. Okay, so tomorrow we'll finish up by talking about the sodium potassium pump and the calcium pump, and see if we can be in some sort of position to do some review. Also, if you have questions about the practice problems I gave you, ask those.